And also I request Professor Saibal Gupta, also from Professor from Geology and Geophysics, IIT Kharagpur. I request our Honorable Vice Chancellor, sir, please hand over bouquet to Professor William Kumar Mohanty. Thank you, thank you and also I request Professor Geology, sir, our Vice Chancellor, hand over the bouquet to Professor Saibal Gupta. Thank you very much, sir. Saibal Gupta. Actually, we have two series of lectures. The first lecture will be given by Professor William Kumar Mohanty, sir. So he is going to deliver the lecture on earthquakes and ground beneath us, and of course, local side response in geological studies is going to deliver that particular topic. And also, Professor Saibal Gupta is also going to give a lecture on the origin of life on Earth, the story from other planetary bodies. So prior to that, now I request Professor G. Rajek say, we're going to give small brief introduction about today's lecture.
Very good morning, everyone. I'm really happy today that we are assembled here for this event. So when I came to know that two of our colleagues will be visiting on their survey around this vicinity, so I requested them to spare additional day so that they can share their knowledge and our students can get a benefit, for which they have kindly agreed. So then I thought which department. So I discussed with Dr. Anand. So since they have wide expertise, instead of restricting it to department, we pulled up various departments. Hence, we are having this on behalf of the Office of the Dean Outreach. So thank you very much, Professor Saibal Gupta and Professor William Mohanty for accepting our request and sparing an additional day. So before I talk about you, let me brief about the developments happening. So April 26th, we started a fertilizer of Sentinel celebrations. And then we have released a vision document with three verticals. One is academic, second one is infrastructure, and third one is outreach. So the draft vision is available on the Andhra University website. So since the fertilizer in April, we have been continuously organizing various academic activities, in particular university level activities. Recently, we had a grand science conclave on 5th September. So then, with the 100-year-old university, we do have constraints and hiccups, in particular with the infrastructure. So we have kickstarted various renovation projects, and we have come up with new projects as well, but it takes time. So we have declared that our centenary spans across 2 years. It is April 26th, we started fertilizer. Then 26th of April, we'll have the big day. Then one more year, we continue. Of course, the construction will continue long. So then, 100-year-old university, we did not have the office of the alumni affairs, so we have a sponsored one. So we are going aggressively. Recently, we have started BTech quantum computing program, which is the first in the country in any institution, a BTech program. So for the National Quantum Mission call, we responded positively and started this BTech program. Then recent NPM call, we have submitted 7 proposals, including one laboratory. So we are very hopeful government is going to support, because one of the key requirement of this NPM call is one should have a EG program, and since we have, sure we'll be getting. We have also recently submitted 7 FIST proposals. So the universities span 2 campuses, north and south. I'm sure you have visited earlier. Um, so we have about 50 departments spread across clusters. We have a college structure. So College of Arts and Commerce, College of Science and Technology, College of Engineering, College of Pharmacy, then College of Law, then College of Education. So these are the clusters. So we have about 14,000 students, main campus, and we do have 304 affiliated colleges. 304 affiliated colleges. It's a vast system. Then our School of Distance and Online Education, we have about 80,000 enrollments. So these are the strength as well as these are the challenges we have to run the vast system. So with infra, 100-year-old, so a lot of challenges. So we have really started. So now the academic front, we are looking forward for collaboration with various institutions. So recently we have initiated a draft which has gone almost to the meeting level right in Kharagpur. We have a lot of ministry organizations located in Andhra University. One of the organizations is Central Ministry of Fisheries. So it's a tri-institute MOU, Andhra University and Central Institute of Fisheries and IIT Kharagpur, Department of Agriculture, Food Technology and Biotech. So what I have come to know is the first round of meeting was held and then there were some uh, um, queries probably. So I'm taking this platform to appeal to you, kindly support that. Then recent NIRF, let me brief. Out of 6 categories, 4 categories we have improved this year. Among the state-funded universities across the country, Jaipur, Anna University, Punjab University, and Andhra University, we are standing at 4. And overall, we are 41. So engineering 88, and then pharmacy 16, law 16. So out of 6 categories, 4 we have improved drastically. So with that, we are aggressively going with various MOUs, academic activities, and we have uh, started a very recent MOU with NRC. We have signed 2 MOUs, and then Indian Institute of Tropical Meteorology. Recently, we signed MOU. So our alumni are looking forward. So we are coming up with a menu card, various projects, and we're going to appeal. So that's a summary from my side. So please, going to colleagues who are sitting on the dais. So it's our great honor that today, privilege that they are here because each one of them are very eminent in their respective areas. They had a vast experience handling both the UG, PG, and teaching and research. Of course, you will see from the profile their contributions in the field of geophysics and geology. And more than that, their scientific knowledge. So that's one thing which I always enjoyed my interactions with both of them. It's we don't want to introduce the speakers because definitely speakers will be introduced. So it's a long friendship, and I'm very happy that they accepted and they are here. So please feel free. Probably while they are lecturing, we should really interact and then try to make use of their presence here. So that's summary. And once again, thank you very much for accepting. Thank you.
My request is to come with the also. I guess the coordinator Andhra University. And I request about today's speech.
Morning, all. Yes, sir.
Professor Vijay Kumar Mohanty. It is my privilege to introduce Professor Vijay Kumar Mohanty, sir. He's an eminent geoscientist and professor in Department of Geology and Geophysics at prestigious
arrival destination. If you are delay on the arrival, so this suggests that there's something happening over there. Of course, some of the geophysical parameters near to the region changes geomagnetic, geoelectric field and risky and geodetic measurement that you are continuously measuring the position of on the earth and both the sides of the fault. Then what you can see that over there there's a change in their position, both in the elevation as well as the distance. And the most important thing is this people bother about it, animal behavior. And most in Japan and China, they have a very well uh, trained. They see that prior to the earthquake, there is a change in the animal behavior. Then why it so? Because animals are more sensitive than us. They are always grounded. And what if there is a change in because prior to the earthquake, there is a small micro noises from over there. And also there is a change in temperature in the ground. So all these things, they feel it and they give very obviously so that it's an indication that there is going to have some thing going on there so you can prepare for it. Even if all these precaution phenomena are there, they're going to lucky enough to have all the precaution phenomena because when you look at the art structure, it's not homogeneous, it's heterogeneous and it's give non-linear. So you cannot morally, you cannot find it quite rightly to talk about how the pressure phenomena come over there. So what is the preparedness in India, how they are prepared till now, what they are doing. So in fact, first donation map of India started in 1935 after the 1934 Bihar Nepal. Then BIS Bureau of Indian Standards, they are the main person responsible to go for this the earthquake donation map. So initially it was 7 zone based on the geology and seismicity intensity map over there. Then, then 1966. So all these things. Then 1970 after the 1967 Korea earthquake, so they modified it. The 1970 things they merged here it was 0 was the starting zone or 7 there, but here they merged the 0. They got rid of that. They came to here that there's a 5 generation map over there. The recent one, but here they took lots of geological, tectonics, and geophysical parameters along with the seismicity to divide the zones. So 2002 onward, the map is consists of lots of statistical data sets available on their hand, looking at the tectonics and source where they are. Based on that, no area is defined as a zone 1. So Peninsular India, after this Latur, Jabalpur, and Bhuj earthquake, they combine there, and it's coming on to zone 2 over there, and zone 2, 3, 4, and 5. This G value to look at is 0.4G, 2.1G, that's value over there. Also, internationally, because earthquake never restricted in a political boundary. So it can occur anywhere. You cannot tell that earthquakes occur in Pakistan, it will not hit in India. Or Indian earthquake not going to hit in Pakistan or China over there. So earthquake globally is occurring. So there is a committee, Global Seismic Hazard, this Global Seismic Hazard map they prepared in 1999. So taking India and subcontinent as a 686 sources, they came out PG values over there. So they use a attenuation model which is known as joiner rule. Attenuation model means you have an equation which consists of some coefficient related to the magnitude, distance, focal cancellation, and the local size. So if you have any earthquake coming over there, if you have no record from that region, you can tell if the earthquake occur over there and how much big downward acceleration can be expected on your side of observation. So they use one relationship which is globally. That may not be useful to the local Indian site conditions. That is one drawback. And also the donation map which prepared within the seismic donation of map of India. And this global seismic hazard program map. So all these maps, they are talking what is the ground motion and the bedrock level. So what will happen in the surface, they have no clue on that. These are useful in the sense that it will give a broad perspective where you have the major earthquake or ground acceleration you can expect. But you cannot quite confidently say that due to the earthquake, how much the PG value going to have over there. So that's why is the seismic hazard assessment at national level sufficient to address the hazard at local level? The answer is very good no, because we have observed in different scenario that what is the predicted ground motion modeling or the hazard maps they are suggesting and what is the ground motion we observe. So if you look at 1995 Japan earthquake, they expected 0.4 to 0.48. So what is the ground motion we are looking at? We observed at 0.7, 0.8, which is very large. And the Gujarat also we have only 0.16 to 0.24. This is also the Algeria, in Iran. In most of the cases, when the national donation map or international donation map giving a value is coming how many times greater than the values they have given over there. So this is the one example is showing over there. Then people talk about the side effects, local side effects, how they're playing a great role and modifying the ground motion at the side of interest. So most importantly, this is the 1985, the Michigan earthquake, which has created havoc in the 360-kilometer distance away from the source region. This is 8.1 magnitude earthquake. That's because the city was developed on a 38 to 50-meter old lake bed before this project. And Nova Great earthquake, the maximum damage occurred in 100 kilometers away from the source zone. In Bhuj earthquake, similar cases you might have seen. In Bhuj local area, the damage is less. But in Ahmedabad, where the new Ahmedabad settlement there, this river channel, the Palo River channel, there they have this major damage suffer over there. In most of the cases, final joining of the seismic wave from the source to the point of observation is through alluvium. So if you have a bedrock and you have earthquake is coming from the below bedrock and you have a basinal structure or sedimented deposition over there, that's going to amplify the ground motion over there. So that's why companies in all these cases, whatever bedrock level ground motion they are giving, this input over there, it will compute through 1D model and refine the value over different. Let's see theoretically what's happening over there, how this basins and thick sedimentary deposition are giving. So most of the site density and SO velocity material near the surface are smaller than the greater depth. Because when you are coming below, as you go to depth, this become more compact and consolidated. So that's why the density increases and the PS velocity also increases. But the energy carried by the seismic wave from the source to the point of observation, that energy is roll the density of the material where it's propagating. This is the shear velocity. This is the ground motion. To combine together, this is known as energy flux. So if you believe in conservation of energy carried by the seismic waves, and we are not bothering now for scattering and damping effect, so this energy should be saved. So if you are going from below, so what happens is rho and Vs they are larger than the topsoil. So to maintain the conservation of energy, that they are going to have a larger ground motion at the surface level over there. Theoretically also it's true that the soil deposition or sediment deposition is going to increase the values over there. So since rho and Vs decreases as wave approach the ground surface, the particle velocity must increase. The ground motion velocity will increase to conserve the energy. So how are the areas they are prone to the side effects? So mostly regions are coastal and river delta region because they are the most region where delta sediment deposits are there. Now the urban areas like in Mexico, we have seen that lake beds there, or in Delhi, if you look at Yamuna change, many times it's pollution and if you look at, there are many pollutions are there, and most of the high-rise buildings in Delhi that's coming on the pollution is over there. So those are the dangerous areas you have to look at. The mountain regions with valley and basins. In Himalaya, because of tectonics, you have large basins are there. And these basins will behave differently when you have a house on the bed of living. Those are the areas in future we have to look very critically over there. The land plates and reclaimed land, this is also dangerous. These are not compact and mega cities close to the seismic hazard, but most source zones like Himalaya, it's only Delhi is 250 kilometers away from there. And over the India, if you look at 51% land area, they are prone to the earthquake. And 80 million houses, that's the report given in 1997. If you look at now how many million buildings there in danger. So that's need to have this local microgeation or very local site specific like ground motion value should be available on the land for the to develop there. So let's see here what happened in the Mexico. This is a one of so Mexico University of Mexico. The source is somewhere here. This city is developed in the world lake deposition here. You can see the thickness of sediment deposits of soft material over there. So the record, you can clearly see within the Unam University is close to the source region, the ground motion record you can see is very small compared to the ground motion recorded at the sediment deposition or the old lake deposition over there. Similarly, when you this time series you plot in the frequency domain, you can see here frequency around 2, that's the amplification factor. You can see here how much amplification is there for certain frequencies over. So each building they are our natural flow. So by the what come story building divided by 10. So if you have a frequency which is at 2, the 20-story building, that frequency of the waves going there and the building frequency is matched together. So that's going to have a resonance effect. What happened the Omega over there, where you have a double resonance, the waves, long period of waves coming from the bush, and you have interaction of the soil and building, and again the ground motion they have the frequency which matches with the high-rise building over there. So based on that, we study the side effects for the three regions. One is your Talche, Calcutta, and Haldia. And if you look at the common factor here, is that thick soil deposition over which the study area is located. This is the Talche basin is the major full deposition there, and along with that you have two major plants near to it. That's the nickel thermal power plant and aluminum. This aluminum company is there. And Calcutta is a major city which is close to the northeast Himalaya, and there is large number of sediment deposition over there. And Haldia is a port city and a coastal region. The most of the sediment deposits there. So what it did, we there are several methods available to find out the side effects, how they are going to behave ground building over there. The most inexpensive and this small time you can do it, as known as horizontal to vertical spectral ratio, H by B ratio, is given by Nakamura. And this is a very if you have a steam equipment, you can move around, you can find out the H by B ratio. Or otherwise you can, as I told you, when the ground motion is coming for a bedrock level, you have a 1D side effect soil deposit there, you can propagate the wave and find out what is the site there. You can go for the 2D and 3D response. Also, you can look at nonlinearity involved on the soil deposition over there, how they're going to behave in the side effects. Let's talk a little quickly of this methods available over there. So what happens here, most of these seismic stations, they are of 3 sensors, 2 horizontal, 1 vertical. And whenever you put a sensor on the top soil, the ground motion application will be recorded more prominently on the horizontal component. and the vertical component is not going to affect more on the this soil amplification over there. So what you do, you just submit the ground motion over there and the frequency domain on the north, south, and east coast component, and take the square root of that, divide by 2, root 2, and divide the vertical component of it. So that will give you what is the prominent frequency and how much amplification over there. This is simplest way you can do. And we're going through the procedure, this is the flowchart, how we can do it. So what we did in the first instance, we have collected 35 microthermal studies along the basin. So what is suggest that when you go from the periphery of the basin on the harder side, the frequency and large frequency there and application is small. So when you go to the middle of that basin, so you have a small frequency, large amplification over there. So based on that, you can quickly conclude that. So without digging a borehole, you can use this the frequency and the periodic frequency and the amplification factor to find out what is the thickness of that. So we can divide into zones over here that where you have the maximum amplification can occur and belong to which frequency and over there. So this is the showing that also you have used along the profile you can find out what is the thickness of the bush over there and the distance over there. Similar way, we did also in Haldia. These are the points of observation of the microtremors. So we were able to find out what are the frequencies of the amplification factor over there. So near to the coast, you can have a large amplification with the frequency over there. As you go inside, it's going to have a higher frequency with much less compared to the coastal part amplification factor over there. So based on that, what will prepare a solution now for the whole year? So this will give you a guidelines where which frequency, how much amplification factor can be expect over there. The other way is that two ways you can go for the estimation of hazard in a local site condition. Either you wait for the earthquake to occur. So there's the moment the earthquake will occur, you know that how much is the ground motion. Or otherwise, you synthesize the ground motion and calibrate with the observed value. Then you prepare yourself for the biggest earthquake coming over there. So we have seen that this is very successfully done. This what here hybrid method. One is your modal summation method. That means on the basement level, you propagate the waves in the basement level. Then on the top of that, 2D layer sediment deposits with all the characteristics of this sediment. So you propagate through that, then in the surface you can find the value. If you are waiting for the largest earthquake to come over there, you never know when the next earthquake will come up. We cannot wait for the next earthquake. The best way is that you model it, calibrate with the observed value, and show you how successfully we have done it in different times. So this is the 1D model, bedrock model. Then you propagated a seismic source over there. This seismic wave generated from the source. The same way, seismograph is propagated in the 2D model. The output is coming over there. So this is the complete flowchart of this hybrid method, modal summation method, and you are getting the seismograph over there. So this is for the culture region. What we did, and the best part is that as much as possible you can have a profile you can generate over there. You have a source somewhere, the source has a characteristic sociological, then you have the 1D model, the bedrock model is there with you, and if you have lucky enough to have some borrowed data or any other algorithm on the topsoil, so you can propagate there. So you can find here the maximum acceleration you can have is 0.53 G here you are getting over there. And the RSR value that means what is the response spectrum for the 2D on the segment deposits or side effects value and the 1D in the bedrock level. So we are taking RSR, response spectral ratio, both in the bedrock and subrock there. So this ratio will give you the amplification and the frequency at which you have the maximum application over there. So this RSA value for the culture is showing that 15 kilometer and this is the 25 kilometer distance from the source, you have the maximum amplification over there. So what we found here also on the microtremor study, we have a frequency band that shows how much is the amplification factor over. So that is the real measurement to the microtremor study and also is synthesized. Please match so quite well showing that this frequency band and activation factor is backing with the synthetic seismograph generator over there. So you can say any manufactured ground region coming over there, how much is the ground motion on the surface level. Then coming to the this is the based on the RSA value, what we did is divided the whole of the Talca region, the low zone where the bedrock level, as you go interior, you have the thickness of sediment deposit going large, so you have a intermediate and a high RSI value over there. Based on that, we divide into three zones to Talca region over there. So again, we are coming to this Calcutta region. Lucky enough, we could be able to get some borrowed data during the construction of the metro projects over there. So use their information to calculate the ground motion over there. What is used here in Calcutta? We have a bedrock model. Source parameter use the Calcutta earthquake in 1964 over there. We use those source parameters as the input for the bedrock level and using the local model parameters, which is BTBS, quality factors, the acquisition factor, density to propagate on the Calcutta region over there. We could able to get it max in points value over there and this frequency band, the maximum application occurring in Calcutta is 0.8 to 1.3 hours. So this will clearly show us how the even if you don't have any actual record now, so you can use the source region and predict how much ground motion going to occur over there. This is the last push study. I am showing you here one of the study we did in the Indo-Gangetic plains because as you know that Indo-Gangetic plains are the very thick sedimented deposits below the Himalayan region and fortunately or unfortunately we have a Narora nuclear power plant is here. So what we did around 300 kilometers in the Narora nuclear power plant project, we did this job. So we take a 500 kilometer buffer zone because when you are dealing with the 8 magnitude earthquake on the Himalaya, you have to take a larger distance. Otherwise, if you don't expect 8 magnitude earthquake, you can confine to 300 kilometers also there. So what we did, we prepared a statement back, taking into consideration all the sources surrounding the Narora region, what are the fault and lineaments there. Then it's a complete flow chart. You have a one flow chart is simulation of ground motion on the bedrock level. So another is there that the local soil condition over there. Based on that, so we could able to get 70 locations where we have these soil condition information are available on the surrounding the their Narora nuclear power plant. So what you did, we observed the Chamoria recorded on the Indo-Gangetic. So these are the three sites we have the earthquake recorded over there. So what we did on that Chamoria earthquake and simulated earthquake, what we simulated at that site, we match the simulation and compare the observed value at different sites. So this is quite well matching both in the frequency level. This is the simulation one, which is recorded in the transverse component and the longitudinal component over there. This is matching well. So also when you frequency domain also you look at your values, the synthetic is matching going the both on the horizontal and vertical components over there. So what we did, using that flow chart, how you have a ground motion coming from the bedrock level, and on the surface we have simulated the values and then propagated on the different border sites starting from 30 meter, 80 meter and 100 meters. So if you take that much of this of soil deposition or road deposition, your ground motion is already there on your hand. You compare or calibrate, then you propagate that in different layers you can find out how they are going to give. So this radar is the input in the breaker plate, this ground motion. Then you can see if you change the values, this thickness of soil deposition over there, so input, then yellow color, then this light blue and color. So this coming from the better playbook, if you have 30 meter, 80 meter, 175 meter, then how much ground motion its amplification you can see. Also in the frequency domain, you have the beta playbook ground motion, you can see that what is the frequency and how much amplification are occurring different. So also for Delhi region, what we did, we have a source to the Delhi, what are the different sources that can generate hazard in the Delhi region. So using those sources, using the attenuation relationship, we have a 3 gram acceleration on the Delhi. Then we have the soil deposit on the 6 meter deposit, geology of that region, and groundwater fluctuation and grade calculation. So we put it in here on a GIS platform. We use the analytical hierarchy process. So you give the voltage, here the voltage is given more to the UGA value over there. So that what you can do, when you don't have much record over there, you can use this information in GIS, you can divide the microdistinction map of Delhi, first order microdistinction of Delhi, you can find out over there. So this is all these things are published in different journals. So if somebody wants to go into detail, you can find it out. So this is the section microgeneration of Delhi. So most of this you can see here in the Yamuna side, very high, and there is one Nala here which has a giving. This is the rich part where you have the less seismic ground motion over there. So this contribution from this study suggests that the microgeneration map of Calcutta, Haldia, Delhi, and the Indo-Gangetic plains. This migration map generated through the present study will be a great importance in facilitating multi-application, and they can use the urban authority policymakers. They can directly use this value or prepare for the next any projects that are coming over there. So that's all from my side. Before finishing, I just because there are so many students are there, I just want to project this slide. So if you look at anybody getting any recognition or awards, this is look like a iceberg. So everybody looks at you, what is your progress in your life? This is an off you will look at. So what is beneath the iceberg? So nobody looks at that, nobody talks about it. So that's the sacrifice, staying healthy, good habits, focus, discipline, mindset, persistence. There is so many daily goals, expensive meeting targets, so all these things are there, which is combined together, give you success story of your life. Which many people will feel they that say that okay, somebody is coming and recognize. If you look at that, the behind the story, you are- so follow this up, you become successful in your life. Thank you very much.
Any questions from student side? Anybody? Geophysics, geology, engineering, civil? Any clarification?
You want to see that slide?
Yes.
Which slide?
Last.
And why? Good.
Yeah, my question is
Yes, can you hear me? Yeah. I'm looking at the magnitude of earthquake, and I'm looking at the distance from the source. You can see that the one with the larger distance is actually having a higher magnitude, at 8.5. So I want to actually comparing the magnitude, I want to know whether it's actually coming from a single source, as in every source, or different source. I'm looking at the magnitude. I'm trying to say.
I got your question. I got your question. So what I showed here, when an earthquake is occurring, generally what is the feeling? If the earthquake is occurring, so how much damage should be done here now? Because here energy carried for the nearest part, energy into more. Because as you move, let the seismic energy propagated from the source, as you go longer distance, because of the attenuation, scattering, then you lose the energy. But in this case, if the source is the site of observation, around, then this the large damage compared to the damage at the source. Why it's happening? That's what my whole of the study or presentation was there. If you have a loose soil, sediment deposit, they amplify the ground. So that is based on that. When you talk about donation map or other map, many times you give the information on a better place. So that's what happened here in Mexico, 350 kilometers away, the township, which is developed on a old lake deposit, where the invasion of it close to the frame. There are no damage because it's star. So this site effects plays a great role, and which is not known to many people. Because people only bother about or they have the information better. So my point is that whenever you are going to have major plants, cities, developed industries you have, you should take care of what is the site going to be a local site you have.
It was an excellent lecture. Yes. I have a question regarding you have calculated the model, done models. So your argument is saying that you are having a structure on the bedrock, the amplitude is less, and the possibility of hazard is lesser. That's what I understand. But there is also the surface wave which you didn't consider in your models. So how does the surface wave, the surface wave would definitely interact during the time of the earthquake, and definitely the surface wave will also have. How did you take the surface wave into consideration in your models?
Yeah, this surface will that if it is a silver question, they can only generate this. And again, this surface, the uh, surface will have a very long period. And those are dangerous. What I'm presenting over, I showed you P to S3 and P to SS2. Those are equivalent to surface. The model which I generated, this is like SB and SS. There are the surface. Essentially,
Now I request Professor Saibal Gupta sir to take up the notes.
Clear enough? Okay, so
Okay, so I'm going to be talking on something very different to what Professor Mohanty actually just talked about. And this is something that is more of a story. Right? It is technical and yet not technical at the same time. It's a story that involves geology, geophysics, it involves other planets, it involves really explaining how life originated on Earth. So, what I'm going to talk about is just a story about the origin of life on Earth. Can we actually think of how that happened? But I'm going to base the story on what information that we get from other books, not from what we see on Earth. And that's really because there are ways in which we cannot interpret this from what we see on Earth. That's why we have to rely on information that we get from other planets. So, first of all, to understand what happens on other planets, we need to understand our planet. So, briefly now, if you look at the world, the Earth itself, the Earth's surface, if we now split the Earth's surface from a spherical projection to a 2D plane of paper, what we produce it. And as you can see, once we do this projection, what happens is that the solar regions, the area, the surface area, is increased, is apparently increased. Now that's because of the projection form that is used, right? This projection form is called a Mercator projection. Now, because of this Mercator projection, what happens is that the longitudes are kept parallel to each other. As a consequence of which, what happens is that all the surface area of the poles is artificially enlarged. Now, what this means is that if you look at the map here, you can see that Antarctica appears to be an enormous continent. Actually, obviously, it's not that, right? It is big, but it's not that big. This is simply a consequence of the projection diagram that you. Likewise, Greenland is big, but it's not that big, and therefore there is an impact, an artifact that arises in which the surface area is actually not preserved in spite of projection system. Now, the most significant thing about this diagram is to realize that the Earth's surface is basically got two types of crust. One is the stuff which is mostly in green, and the other is the stuff that is in blue. The blue part is what makes up the oceans. And those of you who have working knowledge of geology would know that the oceanic crust is actually different from the continental. So the oceanic crust is made up of basalts, and the continents mostly have an average composition of a rock called a granodiorite. Now, this average composition is that of a rock which contains more than 65 weight percent of silica. So it's a lighter rock. So the continents are actually lighter than the ocean. The basalts are denser, and therefore, because they are dense and also because they are thin, the oceans are actually depressed in elevation in comparison to the continents. Let's just take a look at what the difference is between continents and oceans. If we look at continents, the continents are more elevated than the oceans. The compositions also are different. Continents are largely made up of a rock called a granodiorite, which has a silicic composition. A composition which is very rich in a component we would say called silica, SiO2. The oceanic crust is basalt. That is also silicic, but it has less silica. So a basalt has between 45 to 55 weight percent silica, whereas granodiorite has more than 65 weight percent. Now, a consequence of an increased silica content is that the density of the basalt is actually greater than the density of a granodiorite. That is because the remaining part of the rock, the remaining 35% of a granodiorite is made up of heavier minerals. Whereas in the case of a basalt, heavier minerals more or less make up 50% of it. That is why basalt is actually denser than the rock. So that is why we come to this point that continental crust is less dense than the ocean. Now the continents are also thicker. If you look at the continental crust, that is on an average 35 kilometers thick. Oceanic crust is on an average only 5 to 10 kilometers thick. And of course, we have a difference in age. The continental crust can be extremely warm. So some parts of the continental crust can be as old as 4 billion. Whereas if you look at oceanic crust, there is no oceanic crust that is older than 400 years. That is what we call the Jurassic. So whereas we have Archean continents, we do not have any oceans that are older than Jurassic. Okay. So this is the message that we get from the pattern that we see in Earth. But now the question is, why are these continents so important? Now, at some time in the past, the continents were actually built up, right? They were not the first type of crust to appear on our planet. So the emergence at one stage, continents were produced as a consequence of petrology. And as a consequence of that, ultimately they become thick enough to become higher than sea level. When it emerged from sea level, the continents since then, they have played a very critical role in controlling the surface temperature of our planet. And this surface temperature is vital because if the continents were not there, we would not be able to sustain temperatures on the surface of the earth from between 0 and 100 degrees. If the continents were not there, our surface temperature would not, or surface temperatures would not have been hot or cold enough, you can say, to sustain liquid water on the surface. And that has been pretty. The very fact that the continent also emerged from the sea also was responsible for increasing the oxygen content in the atmosphere. And these two factors were critical again to the proliferation of life on Earth. So if there is no oxygen, there is no water, there would be no life. We all know. Okay. But we don't actually realize is the very key role this dichotomy, the difference between a continent and an ocean that plays. If this difference was not there, the surface temperature would not have been under control, and then we would not have had life as we see it today on the planet. So the question is now, continents, how do we name them? I told you before, initially when the Earth accreted, you did not have any granodiorite. There were no continents. You only had a silicic part which had the composition of the Earth's mantle. Now, if you look at the continents in particular composition codes, they are made of silica, just as the Earth's mantle is also made of silica. But the Earth's mantle, the silica content is less than 45 grams. The Earth's continental crust is made up of rocks which are greater than 65 microns. So how do we get this? Now, experimental aqueous petrology since the late 1900s by the famous N.L. Powell. He started the experiments on rocks. And he managed to prove that if you have a silicate mantle, the melt that is produced by melting the mantle, so if you have a solid mantle and we melt the mantle, the liquid is produced, we have the composition of a basalt. And this basalt will have between 45 to 55 weight percent. Now, we assume that basalts, these silicic rocks, these are produced from these basalts by a process called fractional crystallization. If this happens to produce this to have a basalt band, which fractionally crystallizes to produce a granite, you actually need to have water. Unless you have water present inside the magma, you cannot fractionally crystallize a basalt or basaltic liquid to get a granite. You cannot do that without water. That is what we need. So the precise composition of the rocks that can melt produce silicic rocks, that also is not completely known to us. We know that there are a variety of rocks that can do, but which rocks can produce prolific amount to actually form our continents, that we can make continents. So we come to the question of how did the first continents form? Now, to study this, we have to look at the oldest continental crust on Earth. That's the best way to look at it. So let's try to look at where the oldest continents are. Now, we know that the Earth itself, how old is it, by the way? Anybody among the students? 4.5, 4.6 billion years, right? So that's how old the Earth is. But you realize that the oldest rock we have, the oldest rock is only 4 billion years. So for the first 500 million years of Earth history, we have no rock record. That is the part that we call the Hadean. we do not have any rocks on Earth. But why is that? Why do we not have rocks that are there? It's because of these processes called erosion and weathering. So what has happened is over time, even if we didn't have these rocks, erosion and weathering has actually been on the evidence. So we have no evidence of this very old crust that we had on Earth. Right? So the earliest continental crust that we have found, we have no record. We don't know where it is. Now, how do we then circumvent this problem? If we want to find out our continent, how do we actually get it? So one of the ways is that we look for these very rare silica-rich rocks on other planets when erosion and weathering has not. And we know that this may be the case. It could be either our moon, it could be Mars, or it could be Venus. All these three planetary bodies, these are places where you will actually have early crust systems. All of these planets were formed at the same time as the Earth, 4.6. They do have rocks on their surface, which are as old as the planet is. On Earth, we do not have rocks that are 4.6 billion. But on the Moon, on Mars, on Venus, we think we do have rocks around. Well, not Venus, but certainly on Mars, we know that we have rocks that are very old. So we have to look at these early crust and see if there has only been very limited alteration of it. Because on Earth, the presence of oxygen and the presence of water, which have been so useful for us to actually sustain life, that has actually been responsible for removing the rock record. So if we can look at a planet where you do not have that much oxygen or that much water, then it's possible that we might be able to get some clues as to what the earliest continental crust was like, how did it form, right? And of course the trigger for actually using it. So what we will then do is to look for these silice crops. Now when I talk about silice crops, I'm referring to those rocks which have more than 65 growth. Okay, so I'm talking about those rocks which resemble a granodiorite in composition. See, the first thing we need to understand is, are there silice rocks on other planets? Is it possible to find rocks like a granite or a granodiorite on planets other than that? Now, if we look at rocks of this idea, about the surfaces of Mars, Venus, and Mercury, let's say these, we go to spectroscopic evidence now that their surfaces are almost entirely made of this rock called mass. This is very peculiar because if you think of the Earth's surface, 3/4 of the Earth's surface is ocean. So 3/4 of the Earth's surface is actually made up of basalt. It's only 1/4 that is salt. So on other planets also, basalt is the most common type of silice. You have very rare silicic rocks of the type of that we're looking for. However, there are some stray reports that there are some rocks which might have composition with the volcanoes. So where do we begin to look? How do we begin to look for silicic rocks on other planets? In the moon, in Mars, let's say Venus. Is it possible? So let's actually look at the part that is most trace. And these are gold silicic rocks that are outside. The best place to look for these silicic rocks would be on the moon. Now, this is a person whose books used to be read a lot when we were children. So Jules Verne, many years back in the 19th century, he actually wrote a book called From Earth to the From the Earth to the Moon. So he designed what he thought it was science fiction at the time. He devised or thought of man actually making a rocket that would take mankind to the moon and back. So he had thought of this many years back. In fact, many of the details that he thought of were actually employed by the Apollo missions when they started off. It was a very clever idea. Now, suppose we look at the moon. The moon is important because this is the part about which we have direct evidence. We have information, direct evidence for the moon. Because man has landed on the moon, we have got rocks. So it's the part on which we have the greatest trouble. So is it possible to use silicic rocks on the moon without actually getting samples of these rocks? Now, what is the problem? Because among the lunar sample returns that we call them returns. there are no samples, almost no samples of a granite. Except under the microscope, there are two samples from which what we call a microgranite has been used. So it does mean that granites could form on the moon, but it's in very small quantities. So let's just see if there is some way around it. Now the bigger places, because the Apollos have not landed everywhere. So there could be some places on the moon where we do have granite. So how do you? We have to rely on remote sensing techniques to actually get it. The first thing that we need to identify is whether there are specific constructs, things that look like continents on the moon. Now, the first suspicion is from what we see, what are called red spots on the moon. Now, these are spots that are characterized by a higher albedo, means there is a higher reflecting of these spots. And there is a greater absorption in the ultraviolet range. Now, why is this important? It's because these red spots that you see are spots where infrared radiation, right, is less absorbed. And that is actually characteristic of less silicon rich, or sorry, higher silicon rich. The other important thing is that they have higher podium concentrations. So the spectra also tell us where on the planetary surface do we have higher concentrations of certain elements. And thorium is one of those elements, which is very important in that because elements like uranium and thorium actually move concentrated in state and vanadium. So in CDC crops. So if there is more, there is a greater chance that we probably have something which is more CDC. So we see that these zones actually go inside higher zones which have higher podium concentration on the moon. And then we go to the most important. These are particular spectra on the emissivity spectrum. So any in physics in high secondary, you would have heard of the term emissivity. So when you're receiving the emissivity spectra, so some of the wavelengths of light are absorbed and some of the electromagnetic radiation is transmitted. So what you'd actually see or reflected, part that you're actually seeing is a part that was not absorbed, right? It's a part that was emitted, spectra that was emitted. Now in this case, there is a feature called the Christensen feature, which actually depends on the presence of the SiO bonds. Now, the Christensen feature is an absorption by the silicon-oxygen bonding bonds. So, the higher the proportion of silicon and oxygen, because of that, you can have greater absorption, right, of this particular wavelength, right, leading to a particular feature called the Christensen feature in the emissivity spectra. The lower the value is, that is, if it has got value that is less than 8, it means in that sense that there is a possibility, strong possibility that these blocks could very silicon rich, possibly greater than 64 waves. Now, this is a Mercator projection of the moon. So the spherical surface of the moon is just flattening it out into 2D. Now, as you know, there are two parts of the moon. The side that we can see is called the near side of the moon. The part that is on the other side that we can never see is called the far side. Now, why is it like that? It's because the moon is smaller than the Earth, and the Earth's gravitational pull is much greater. Because of that, the moon is not able to rotate on its axis. So the Earth's gravitational pull keeps it used so that it doesn't rotate. We call this the tidal force. So the tidal force of the Earth is so much greater that the moon itself is tidally locked. Okay, it cannot rotate. We can only see one face of the moon. So the face that we see that there is a big dark portion on the part, there are lighter portions. The lighter portions are actually higher rocks. These are higher. These are made up of a rock called anodosite, which is radioactive cells. On the other hand, the dark regions you see are mostly basins. These are craters, these are cratering units. And within many of these craters, you have basalt magma, which is two. Now, within these, if you count in all the spots from which we can identify silicon and you plot them, you find about 12 features. Mostly 11 which are actually in the near side. And there's only one where the Chinese have landed on the far side, which is called the Compton Belkovich volcanic complex. Now, I'm going to be talking about just one, that is this one, W, which is called the Wolf Crater complex. It was one that hasn't been worked on a lot, but something on which
Kharagpur actually did a lot of work. Now, this is what this W feature looks like. It's called the good data complex. This is what we're using. So this is the greater V, this is the greater flow. We have another part which is adjacent. So it was first suspected to be CDC in nature, at least part of it, in 2017, but that was just a suspicion. It was just an action. So we tried to use a number of remotely sensed methods from all the missions, lunar missions that have been sent. Some of them were actually missions that have landed on the moon. Most of them were orbital missions that actually took photographs from the remote sensing data from the moon. And these included a number of instruments on different aircraft. So there were different measures, missions. So you have the morphology, that is what the topography is like from a number of these missions. The composition, which was actually obtained from a number of missions again, some of them were NASA, some of them were the European Space Agency, some of them, in fact, were very important. For example, N was one of the most important missions that was sent, because this was on board. It was a NASA instrument that was on board Chandrayaan-1. Okay, so most of the important information we used was from this end. And of course, we have the grain mission. This was the gravity data. And of course, the analysis, once you get the spectrum, you have to have analysis techniques. So what they did was we used a number of techniques to follow people like what Prakash Chauhan and Gatti actually did in the past. Using this, the spectra were actually resolved to extract information. Now, this is look at the morphology. So this is the crater. We studied the walls, and what we saw is that look at this. Craters normally on the moon are formed by impact of a meteor. But if you look at these craters, we had evidence that they are bounded by faults. Now, this is more characteristic if there was a volcanic eruption, and following the volcanic eruption, the whole place collapsed to form a crater. So this is called a caldera. Something that is formed in that way is called a caldera. So these features, we found features that are characteristic of caldera collapse. So it was not really impactful. And there were several stages of this collapse. It doesn't collapse all at once, it happened in several stages. Not just that, if you look at the side rings of the crater, you can see lobate flows which are actually going down the floors of some valleys called that we call gravity. Now the central part of it was mostly filled with basalts, and these are called mare basalts. Okay, so the center of these holes on the surface of the moon are called mares. Now the crater rings themselves are elevated with respect to the crater. And it's clear that this crater was not formed by the impact of a meteor. So the only other way we can form a crater of this dimension is if there was a volcano in which the top collapsed, just as we see on many thousand years. So essentially, we can include the involves of volcanic. Then what we can do is to use the composition. So again, from a number of instruments, dominantly NQ, and there is a divider, we get, for example, this criticism. This feature actually is this absorption line that we get. This is a criticism. And as I told you, if rocks and ice are contained, then the criticism feature will be less than 8. Now, if you look at the crater complex here, you can see that the ring has values that are less than 8. Whereas if you look at the interior and the outside, right, they have values that are much higher. This means that the ring seems to be seriously higher. Whereas the more, and this part are more characteristic of what you would expect to be associated with that. And again, if you look at the nature minerals that coincide, now this is the train, this is the ring zone. So we divided them into 2 ring zones, and we had different flow zones here, which were all at different levels. We find that there are a number of pyroxenes. Now these pyroxenes include both low calcium orthopyroxenes, pidgerites, and also medium calcium clinopyroxenes. Clinopyroxene, we don't really see it on it. Okay, there is a gap between the clinopyroxene composition. On the we don't see that. Right? We have compositions across. So that's travel across you. You bring the series groups, you also begin to see the association of a mineral called spinel. Now, spinel is that here. Now, that mineral is also associated. And this can only be formed in association with silica under special circumstances. So we know we have pyroxenes, we know we have scalate in association with the silicic rocks that we see. Now, what about the gravity strands? Because we know silica itself is low density, and therefore, if you have a low density rock, then the gravity anomalies will actually be lower than if you had latex coral grain. Okay, which are heavy. So the gravity anomalies again tell you that if you actually combine all of this, you can see that most of the crater form, right? You can actually get the anomalies that are associated with the crater roots. The most important is the polar gravity anomaly. That we have a high mass filter that gets rid of most of the gravity anomalies that you can see associated with crater depth, and then through a number of manipulations that you can use of the gravity data, we can actually invert that to find the crustal. And we find that below the crust here, we can actually go up to a depth of 30 kilometers. Now, all around it, the crust is only about 16 kilometers. But just there, where you have the silicic rocks, line chart, we seem to have silicic rocks that are about 50 kilometers. Now, what about the age of we don't have any aircraft rockets carried up from them. We don't have any samples, so we can't date them very well. But we have some planetary bodies. Is that you date planetary bodies by counting the frequency of craters on the surface area of the planet. And these are we have calibrations according to which we can actually compare and guess the age. For the calibration is actually quite well done. Now, as a result of this, you can see that the rim zones of the craters, RZ1, RZ2, and RZ, these have ages of 3.6 to 3.8 billion years. I should say 3.8 to 3.4. Whereas the Mare basalts which are in the floor, in the rim of the crater, the floor of the crater in the central part, these are much younger. These are only 2 billion years, suggesting that basalts actually erupted much later. So, it means that the elevated crater rims of 3.8 to 3.6 K, the Mare crater floors are only 2.6 to 2 K. So they are much, much younger. So we have old 3.8 to 3.6 K old silicic rocks. Now, please remember this number 3.8 to 3.6 because it comes important at the end. Now, if I get all of these together, if you look at the rim of the crater, you have these viscous lava flows. You have collider collapse structures in any direction. We have some post-collider domes that also happens in volcanic constructs. We have compositional constraints in the below crystalline feature. We have low iron abundance also. It's also valid from and overall the amount of native minerals in this particular part is low. And then of course we have these low gravity index. One of these seem to convert the idea to create a complex with a silicic volcanic complex. Now you might wonder, just find out a spectra of quartz and feldspar direct and then compare. The problem is that the spectra of quartz and feldspar are actually not clear. They are very broad spectra. And from those spectra, you cannot identify quartz and feldspar with confidence. That is why you need other sources to guess at how much silica there is there. That's why we have to rely on the scientific system. Now, how this silica rich feature originate on the moon? Because this feature is also dry. Along with the silica rich rocks, there is no evidence of any hydration. We do not see any hydroxyl groups. So what we see is radiation spinel in the silicic constructs. And this suggests that you had silicic magmas being produced by crustal melting due to basaltic undergrade. So some kind of rock which contains olivine and plagioclase. If that kind of rock can be melted, you can actually produce silica in addition to some silicic rocks. Now most of these, if you look at these low calcium stars, it's not very iron rich. The other possibility, something called silicate liquid in silicate, that also is something that we cannot consider on the moon. So the high thorium content also is also counter the silicate liquid in silicate. So the only model through which we can actually explain this is really by considering older rocks which have been drilled. So we think that the silicic magmas were formed later by the crustal melting of even older crustal rocks on the moon. This team actually worked on this problem.
And then seems to have happened is that early in the moon's history, one of the moon's surface was covered with a magma ocean. So there was a magma ocean which was all basaltic liquid, and that solidified to form anorthosite on the top. So once that happened, later on in lunar history, around 4 billion years or just younger, just after, there was something called a lunar mantle overturn. That is, there was a density stratification inside the moon, and the whole moon just turned upside down. This is not something that is unusual. It does happen on Earth in waves. It's quite common. So seasonally, the bottom of the denser part is at the top actually subsides down, and the whole lake actually inverts. So this is an overturn, and you can actually see that such a thing had happened on the moon. Now, whenever such a thing happens, magma is going to be produced whenever deeper rocks come rapidly up. Magma will be produced by what is called deeper. But this magma may not be able to make its way to the surface of the moon. The only way it can do that is when the crust of the moon is thinner. And the crust of the moon will be thinner wherever there is a cratering. So if there is a crater impact, the crust would be thin. There will be fractures developed. And the magma that is connecting at the bottom will be able to come to the surface. Now, between 4 billion years and 3.8 billion years, planets, we know that there was a bombardment of meteorites on all the inner planets. This is referred to as the late heavy bombardment. And in fact, if you look at the age of the oldest CC crops, it actually coincides with the end of the late heavy bombardment. What is interesting is this is also known as the age of the oldest continental crust that you see on Earth. That is also around 3.84 billion. So it actually coincides in age. So we can actually speculate what you have actually formed the first CC construct also a similar process where what went first. If you have bombardment, you should sustain a large continent, you can bombard. You have to sustain gravity mass. And then if you have to do that inside a CC planet, you need water to be pushed into depths into the mantle. Unless you can push in water into the depths of the mantle, you cannot actually do this. The question that rises then, the moon doesn't have so many CC points because the moon is too dry. But is there any other planet on which we have some evidence that there was surface water in the past, at least sometime? But there is one. And that planet is Mars. And the internal it's got a crust, it's got an outer layer, it's got a core. It's actually quite similar. Now, Mars is this. It is fully if you count from the sun. So this is Mercury, this is Venus, this is Earth, and the next one here is Mars. Okay, so Mars itself is important because we need to know a little bit about Mars to compare it to comparison. Well, Mars is smaller than that's 6.4, 64,000 kilometers, 6,400 kilometers, right? In contrast, if you look at Mars, it's around 3,400 kilometers. That is what the range is. Mars is also lighter than the Earth. The Earth is the densest planet. It's got a density of 5.5 grams. The average density of Mars is around 4 grams. It's light. If you look at the surface of Mars, right, it is also basaltic, but it is intensely cratered. Okay. And the oldest crust, unlike on Earth, the oldest crust on Mars is about 4.6 million. So we do not see 4.6 million year old crust on Earth. We also gas. And of course, there is also a thing called a crustal dichotomy. I can see on Earth elevated portions, lower portions. You also have a dichotomy on Earth, but that is geographically distributed. You have the southern part, which is higher, and a northern part, which is just flat, plain, slow. In fact, if you look at a vertical projection of Mars, this is what it looks like. So the southern part of Mars is all highland, it's elevated. And it's about 2 kilometers higher than the northern part, which you always know. So there's a difference in height between the northern part of Mars and the southern. Now, the question is that we need to answer with respect to Mars is, was there ever water there on the surface? And if there was water, is it possible that there could have been life on Mars? If there is,
how do we make room for it? Where do we search? And we are yet to land. So in that case, even without landing, is it possible to identify, what these signatures are? What are we looking? How do we find this? So for this, it's precisely answer these questions that NASA started the Mars exploration rovers. And among them, one first that actually made a landing was this rover called Opportunity. Now, this was actually selected because what Martian surface, that Mars is called the red planet. And the reason it's called the red planet is because we thought or we think that the red color is caused by rust. Just as on Earth, if you have iron lying around, it will rust on the surface and it will be reddish. Similarly, the whole of the Martian surface is a reddish. This which spectra seem to give the spectrum of hematite. Whenever we get the spectra that is characteristic of hematite, that seems to suggest a place where we can actually look for gas. Now, to bring this demonstration was actually directed to that spot from where the signature of hematite was very strong. So on this Martian surface, and the central part, there is a place called Meridian that has the strongest signatures of hematite. And their opportunity landed. Once it landed, strangely, the first thing it noticed is that it landed on basalt, but on top of the basalt, it noticed that there was sedimentary. Now, these sedimentary rocks included evaporites. Now, evaporites, chemical sediments, they form when water vaporizes and things that were in solution are actually precipitated. So you see evaporites that were reworked by wind action, and this overlies the basalt. If you look at what it uses, it's called the Burn scale. If you look at sedimentology, all of this, the characteristics are such that it seems to have been sediments that were transported both by water and by wind. Aeolian winds wind. Some request means that there was wind. So that means there must have been surface water on Mars at one particular time, or you could not have got these things. Even more important is when it landed, it was expected to find hematite. And what was good is that the genetic that it was of a mineral called Geology. Now this is hydrous silicate. And this particular silicate, it found this in association with other calcium and magnesium sulfates. Sorry, geosite is hydrous sulfate, and it is important because of particular characteristics. It is 10% of the outcrop, it just covers 10% of the. And then, although it was initially just discovered there, after that, many of the rovers have been found that came out jarosite at many parts of the surface. Now, this is the formula of jarosite. We test that there is potassium and sodium here. This iron here is ferric iron. This is sulfate. Now, sulfur, when it's oxidized, it becomes sulfate. And then you notice that it has 6 hydroxyl groups, which means that there must have been water. Otherwise, you can't get this. So, the presence of water, you need oxidizing conditions. But also, to precipitate this, the water has to be extremely acidic. Its pH has to be less than, otherwise, you actually won't form this. And on Earth, this is extremely rare. Now, we do not see it because these low pH waters are very difficult. You can't actually sustain them. If there is basalt around, the low pH will react with it, the water, and itself will become more acrid. So to understand this on Mars, now what we did was to look for sites similar to this on Earth, whether we can get jarosite on basalt somewhere on Earth. And indeed, there is one such locality in, and that is the Kutch district. So, past the Tropic of Cancer, if you go across, then in this particular part here, this kind of green is Deccan basalt that you can see in the Kutch district of Gupta. And here, on top of the basalt, the Deccan basalts, there is a formation called the Mataruman formation. What you can see there, the succession is that you have columnar basalts, Deccan caps. The top of the Deccan caps are weathered, spheroidally weathered these rocks. And then on top of this, you have these layers of sediments within which you see these fractures within the cell. This is the belly. So these are fractures, so both parallel to belly and across belly, you actually find these yellow crystals. Now, how do you find things like this? If it's only from fractures, the only way you can explain is that water percolated both parallel and then along. So it must have formed, these yellow crystals must have been precipitated after the rock formed. Otherwise, you cannot fracture the rock and get the water to percolate. We collected all of these samples from these parts. This was all done in collaboration with ISRO. And then when we looked at this mineral was, we found to our surprise that it was calcium. Exactly what we find on Mars in very similar series. So these are of spectra. So this is XRD, right? This is the FTIR spectra. Right? This is what's called the very visible and near infrared range spectrum. So all of these actually show us, confirm to us that you had jarosite. The question is, why did jarosite form on Mars? What was the reason that you can see? It's secondary. So it did not form during the volcanism, formed after the volcanism. But jarosite has another property. It can only form when it's not completely submerged. It can form only when it's just moist, right? Just water limited conditions. So we the Kutch in the past had sediments and Kutch is drying after. So Kutch is now a very arid. So this transition of this Kutch from humid to arid, this was possibly linked to the formation of jarosite in Kutch. What this means is that jarosite formation in Kutch we could determine that it was when the conditions changed from humid to arid. So when it became, that was the time when jarosite actually precipitated quite a bit inside the uppermost formations that we see on Mars in after the Deccan. So these are the work people who did most of this work on the jarosite. And what we interpreted this to mean is that if this is what we see on Earth, on Mars also, the jarosite that was detected by Opportunity and other rovers, it must have formed when there was water on the surface, and that water at some time in the past evaporated. So that was the time at which jarosite was visible. So it actually is a signature of the drying of Mars. So it is just proving to us that on the Martian surface, you probably had a lot of water at one time, all of which dried up, and that is what you will actually see in the presence of jarosite. Now, we know that Mars once upon a time had liquid water on its surface. Because it was jarosite, it's 83 plus, it must have had an oxidizing atmosphere. So you had oxygen in the atmosphere, you had water on the surface. The next obvious question is, was there ever life on Mars? That's what we need to understand. See, the problem is that life needs just not just water and oxygen, it also needs a few other critical elements. Now, what are these elements? You need to have carbon, you need to have hydrogen, you need to have oxygen, you need to have carbohydrates. You also need sulfur, because sulfur stabilizes protein structures because it forms disulfide bridges between those amino acids that contains. Okay. After that, of course, you need any of these elements. Boron, molybdenum, uranium, vanadium. Why do you need them? Because what these do is that when you form these amino acids to convert amino acids into ribonucleic acids, that is to RNA and then to DNA, you actually need to stabilize the chains. Only the presence of these elements, very minor quantities, can enable you to stabilize these elements. Otherwise, you can't do it. So, borates, now they complicated element can have boron, molybdenum, germanium, and vanadium, but they have to be present as borates, molybdates, germanates, and vanadates. That is, as oxides. Unless these are present as oxides, you can't stabilize. So these stabilizing role in forming these organic molecules. These organic molecules include something like ribose, or 5-carbon pentoses, 5-carbon sugars. All of these are vital to the formation of. Now, on Mars, then, when people realized this was the case, they sent this one, which is still doing its work on Mars. This is called the Perseverance. And this was sent to study for evidence of either present life or life which may have existed in the past. And what it is doing now is that it's testing out new technologies which can aid future missions to find out, if something ever was. But how do you actually locate this? How do you know this? We do this now. Signatures. Now, perseverance really doesn't know exactly what it's looking for. So we know what are the environments. What we were trying to do was to think of what kind of signatures would help to the perseverance timeline. So it needs to look for environments that uncoast or might once are coastal, like that are similar to that. So we know now on Earth that the earliest part, it was suspected that earliest life began beneath the oceans near hydrothermal vents. These were energy sources. That was where we think that the earliest life was. These hydrothermal vents associated commonly with mid-oceanic lakes. This is the place where we think early life would have. However, the problem we now realize with continuing studies is that if you have continuous submergence, if all the time the thing was underwater, in that case, that actually inhibit polymerization. Nucleotides need to polymerize to form amino acids. Polymerization will not take place if it's continuously underwater. So what needs to happen is that we need to provide water. Provide water, light up. It should not be continuously submerged underwater. That means that it's difficult to conceive life having originated underwater. So what kind of cycles that are you looking for? What is more conducive to the formation of nucleotides is alternating with base spreads. Okay. But this will only really happen. This will only really happen on continents. You can't expect wet and dry alternation inside oceans. It's always wet. So you need to have wet dry alternation. In that case, in continents, what are the potential localities? We need to know. It's likely places because you need an energy source. If you get continental hot springs. So whenever you have hot springs, their deep energy would actually provide potential habitats. Because now we put in continental water melting ponds. That is the water comes in, collects in the hot water collects in a pond and then dries up. So you have wet dry states. These are near hot springs. So these also finally need to be associated with the critical elements that are needed to stabilize. Now, in order to do that, we need to characterize such hot springs on Earth. We need to identify the spectral signature because we will then know what perseverance needs to be for on Mars. So what do we need to look at? You need to have any of these hydrous sulfate signatures. Hydrous sulfate annuline, calcite, gypsum, etc. Hot springs are characterized by the elimination of opaline silica. It's a very important mineral that silica that we can see, which is actually characterizes precipitation around hydrothermal vents. And then, of course, borates. Borates very commonly found in evaporite. And elemental boron has been reported from him. We do not know the boron is in the form of borates because the instrument which can identify borates that is not there on the rovers. So we need to identify these signatures. Why is it important now? Boron is one of the key elements. Because this is what controls the reactivity of various prebiotic organic compounds. So these include petroses, hexoses, pentoses. What it does is that it stabilizes carbohydrates and it also stabilizes proteins. Now, boron is being found in a Martian meteorite, and you also find it on Mars. There is a place called Gay crater. You can actually find calcium sulfate in fractures. On Earth, Puga, for example, in India, the Puga geothermal. This is a great place to look for. It's a habitat which is in the rock. This is what it looks like. And there you can actually find copper and silica and sulfates, which are precipitated from the hot spring. We have sulfates here. This is prismatic gypsum, which we actually photograph with ACM. And then you have spectra, which actually characterizes the presence of gypsum, right? And opal also. Opal is gypsum. So you can get spectra of both from Kubra itself. You also get hydrosulfates, which testify to the wet dry cycles. Signified by the hydrosulfates. You have some alunite also from. And then finally,
That's the indices of volts. So we can see the spectra from which we can identify volts. Now, it is important when you're doing spectroscopy, individually they don't respond. You see, all the spectra appear together. You need to deconvolve the spectra and identify what is contributing, what bonds are contributing to what kind of. So using them, we can now, with the whole assemblage we've got to put up, that helps us to actually characterize and identify. Okay. Very close to being done. So these are borate signatures, all of which we can see from food. And therefore, once we know that this is the assemblage that is needed to detect life forms. So these are, Puga is an excellent, we think, a very good terrestrial analog. If you want to understand Martian evaporites, borate mineralization, and all of these together, if you want to identify where life forms can be on Mars, these are also places where you can actually look for early life forms on Earth, if you can identify ancient hot springs of it. So ultimately now, let's get back to the moral of the story. I don't think this is working either. So what we do is, if we have to survive on this planet, a number of factors it needs to converge. Now, our surface temperature had to be such that it could stabilize liquid water. For that, we needed continents to form, and we needed the continents to be above sea level. Now, we know that the continents are silica-rich rocks. They can form on planets with silicate interiors, but they can form by two or more stages of partial melting and process. Now, the earliest continental nuclei, they may not have needed water. These could have formed from early meteoritic nucleus. But on Earth, if you have these large continents that we see, you ultimately need surface water that has to go into the surface. Now, this surface water, it needs to be present, it needs to circulate into the battery throughout geologic history. In other words, this needs plate tectonics. So that is the only process which will do this. And of course, you need an energy source, and you need a number of critical elements together for life to come together on planet. So in other words, this image is one that I really like. It was taken from the moon, and this is an image of the Earth. So it's an Earth rise. You just have to think, if you're standing on the moon, if you're looking at this photograph, imagine yourself on the moon, looking at the Earth. You realize how very lucky that we are on this planet, because that is the only place where all these factors have come together. Mars couldn't sustain life, was not a the moon didn't have water. Everything somehow came together on Earth. It was difficult. Thank you. Any questions? You're all tired. Yes.
Thank you very much, Professor Saibal, for your excellent presentation. Being a geologist, I would always wonder about these secrets of no. So, last one. It's not a question, kind of my idea as well. Initially, you said the silicic rocks are formed on the earth. They are not found as larger as on other planets. You said we need a component of water for the differentiation. When we take that concept, in the Precambrian, we have a lot of silicic rocks. Do you mean to say that we have enough water in Precambrian?
Well, see, the first part of the Precambrian is not accessible to us. So the Hegelian part, we don't know what happened. Now, to form the earliest one, then even on Earth, a recent paper, this about 2 years ago, so it actually demonstrated that one of the oldest silicic rocks we had on the planet was where a meteorite impacted somewhere in Canada. And that particular part, that CDC crop that was generated there by the impact, that was 3.9 billion years. So what I'm just drawing is a parallel. I think you need a nucleus initially to get water into the mantle because we don't know how efficient plate tectonics was in circulating water in the early. So, or whether plate tectonics operated at all, that is a question of debate that I'm not getting into. But the thing is that you need to introduce water inside the mantle to create the phase diagram conditions required for fractionation of basalt to granite. Now that happens at higher pressures. It does not happen at low pressures. So on the surface itself, you need to have a nucleus. That nucleus has to be on possibly in the absence of water. So the continent or the construct that we identify is an anhydrous landmass. So this form, the association with spinel tells us that it possibly formed by the partial melting of crocodile, which is there on the lunar surface. Only the sky. So that combination helps. It may not be the only combination, but there could be others that could form the nucleus. Now, because there was no circulation of water into the lunar mantle, we did not get subsequent fractionation of water that can build up the continents from there. What I'm trying to show as a speculation, this is only speculation, is that maybe on Earth also it began the same way, because the oldest continents on Earth are also 3.8, around that range, 4 to 3.8. Same on Mars. We don't know how old they are on Venus, because there are recent reports that there are possibly some granite-like bodies on Venus. We don't know. So this future missions will only tell us.
Okay, thank you. And you said these craters of the moon. At one point of time, you were telling they are maybe a volcanic craters.
Not all of them, the Wolf crater is. So many of these craters are actually
The
intact.
wind crater is almost 25 km diameter.
It's more than. It is more than that.
Can we expect that kind of that big volcano?
That's the question. The largest volcano we see in the solar system, Olympus Mons on Mars, that is much greater. That's more than 100 kilometers away. So the thing is that exactly how large the magma body can be, it's difficult to say. And in fact, at one time, as I told you, the whole lunar surface we think was a magma ocean. In that case, the whole surface essentially was liquid. So, I mean, it's a very pertinent question, but I think that depends on the heat budget at that instant. That is what could pay. So,
My final question. This Mars surface is full of hematite. Inside is there. So even if you see
a
the
lot of it is there.
rover and curiosity, you can see those pictures. These hematite bodies. What is the, how do you feel the process of its formation?
I think the process for this is my feeling. The process is very similar to Earth. I think it was simply rusting of the surface. So it's the same thing that happens when garnet is rusted. Rusted, it forms red streaks.
There is the iron oxide.
So it's iron oxide. I think it's exactly the same, but it needs to be oxidized. I think the Martian atmosphere once had a lot of oxygen.
Now it is not there.
Now it's not.
So,
So Mars lost its atmosphere.
the source rock must be
The source of
source rock.
that's all. So it's just very iron rich. So it's okay.
In the same way, when you talk about moon, you have anodesites, you have basalts, and there is no actually what you said this oxidation. No oxygen at all, no atmosphere.
None at all.
The reason for that.
Well, the size is a big factor. I mean, to hold on to an atmosphere, it has to reach critical size. Mars did have that critical size. Now, why Mars lost its atmosphere is a very interesting question, and I think Geology found that time. So the idea, I mean, this is again speculative, but there are some indications on Mars's surface that we can see magnetic stripes. So it means that once upon a time, Mars must have had a magnetic field. So like the Earth. Now, at some time in the past, Mars actually lost its magnetic field, possibly because the core crystallized completely and it would come back. Once that happened, Mars lost its magnetic field, then the solar flares which would come in periodically we have, these solar winds coming in. So usually on Earth, for example, our magnetic field protects us. So if Mars lost its magnetic field, there would be nothing to protect the atmosphere of Mars from being blown away by the solar wind. So that is the idea, that when it went away, the pressures fell, all the water escaped also, because water had died because of the absence of water. So that is possibly the time when oxygen disappeared from the atmosphere.
Thank you. Thank you.
Because the question, it might be a little bit different. None of the ages what you have found on moon, Earth, or anywhere, you have not found anywhere more than 4.1 billion years.
No, we have. Yes, I mean, there are ranges of 4.5, well, not 4.5, 4.4, etc. are there. Because the moon formed around 4.5 or so. That's what
Your results show.
these are the
Only
series rocks. There are nanoxides that are,
Yeah.
there are 4.1, 4.2 nanoxides on the moon. But I mean, on Mars, for example, 4.5 year, well, almost 4.6. You actually have basalts.
So I have one more. You were talking about the lava, magma. You are just trying to have the same model as Earth, where it has crust, mantle, and core.
Well,
Because
we are pretty certain.
Yeah.
We are pretty certain that they have crust, mantle, and core.
How come you have come to this conclusion?
Well, for example, if I ask you, how do we know that the Earth has a core?
Because of seismic activity.
We knew this.
Seismology.
We knew that the Earth had a core even before seismology. And that is because plain and simple density calculations. So if you take density wise, right, we know the bulk density is 5.5 grams per cc. We have known this for at least 2,000 years. Even Aryabhatta knew this. And this is even older. And the reason we know this is GMM by R square. If you do the astrophysics of it, you can calculate what the mass of the Earth is. Those who believed that the Earth was a sphere knew what the radius of the Earth was. Eratosthenes found the energy. So you knew what the volume of the sphere was. You have the mass, you have the volume, you know what the density is. If you take the surface rocks, basalt, granite, etc., compress it to a depth of 6,400 kilometers, the Earth's bulk density can never become 5.2. It will be much less. Unless you have something which is denser inside, material that is denser, you cannot make the bulk density to 5.4. Now, this bulk density, what material? This is not a unique thing, it could be anything. But if you look at meteorites, which you think are what made up the early solar system, then you have meteorites, the iron nickel meteorites have a density of 5.7. Those meteorites, if you think of making up the core of the Earth, the bulk density you can actually. It's the same logic that is used on other planets also.
Well, and also, geophysics department. I have suggested many possibilities. According to nebular hypothesis, we know that all the planets are coming from cloudy. Then all these planets are formed in the same, that is 4.5 billion years.
Yes, I mean, at the time the sun formed, the planets also formed.
Yeah.
So the whole solar system, 4.6.
So overall, all planets are the same age.
All the planets that we know of, right, that accreted when the solar sun accreted, they all have the age of 4.6.
Or any difference is there between
So far we don't.
we don't know.
So far we
That's
don't.
what we have.
I mean, this is a sort of assumption you can see based on astrophysics. Right? The model, as so far, the model seems to work that it's 4.6. All the meteorites we get from the asteroid belt, when they've been dated, the oldest ones we found, they're all 4.6.
Thank you. Thank you.
Recently, Matthews. Very happy to say that we have on many things, I mean, many new technology we have listened from you, and it is highly thought-provoking. My question is, I mean, actually, you have been telling about the drying of surface waters on Mars. That means water existed once on Mars.
Surface of Mars.
Yeah, surface. So what the reason for drying up of this surface waters and what what could be the duration actually?
What will be the duration?
Especially for this process to happen.
See, there are two things. One is the first part I actually mentioned to the professor who was here. Yeah, so the solar, basically what Mars probably had a magnetic field. When any planet has a magnetic field, it will be able to protect. Magnetic field creates a shield around the planet. And that protects the shield from the ionized particles which come in the solar flares and the solar wind. So at that time, right, I mean, Mars was protected by its magnetic field. Now, Mars lost its magnetic field. The magnetic field most likely because the core crystallized. If the core crystallizes, there is no dynamo. And then the magnetic field will collapse. According to our prevailing theory, that is what we think. This happened on Mars probably around 3.8 billion years. At that particular time, at that particular point when the core crystallized, the magnetic field, disappeared. That is the point where the protection for the Martian atmosphere was lost. So if you have a solar blast from the sun, which happens to you, so there is nothing to protect the atmosphere. It's like a fresh gust of water, it clears the pipe, it blows away the atmosphere. So as soon as you blow away the atmosphere, suppose you have a particular atmospheric pressure here, suddenly if I decrease it to zero, a drop of water here will immediately dry up. Because the pressure is decreased. Right? That is exactly what it means. People are hungry. So,
On behalf of Geophysics Department and Office of the Outreach and on my personal behalf, I'm proposing this of thanks. I thank all the participants from the Geology Department, Geophysics, Meteorology, Oceanography, Civil Engineering, Geoengineering, Geography for your active participation. I thank Professor Kumar Mohanty sir for delivering expert lecture. Really, sir, it's a great lecture. It's inspiring to our students. Thank you for your lecture. I thank Professor Saibal Gupta sir for delivering expert lecture and inspiring our students and faculty. I thank HODs of Geography, Geology, Geophysics, Civil Engineering, Meteorology, Oceanography for attending this lecture and deputing your. I thank special thanks to HOD of Chemistry Department for providing this lecture hall. Finally, I thank our Honorable Vice Chancellor sir for arranging this lecture. Thank you. Thank you. Thank you.